let's see. As usual, I want to review. And then if you recall, what we're doing is a two-state problem where we're going to allow population from a ground state to an excited state. There's X number of particles, and we can allow any number of them to go into an excited state. And already I can tell you that those aren't electrons. Electrons can't do that. So again, these are the kind of little things you ought to know off the top of your head. Anyway, before I get back to that, so remember I tailed off last time before I finished that. Again, I always review, and hopefully you do too with your own students. So to remind you that we have paradigms of statistics. If you're going to ever set up a model, here's kind of the point of this review, other than it's a review. If you ever get into solving models, and not all of you will, some of you will take experimental data and then just, that's it, to be blunt. That's the majority of you. But sometimes you can come up with models, and that's fine. Human creativity is incredible. But what if your model simultaneously allows internal energy and temperature to both fluctuate? I don't know how you do that, but I don't know, somehow you do. What if that happens? Is that good or bad? It would be bad, by the way, because you can't do that. That means that you can set up the model. I can have a model of my cats chasing a laser. I mean, whatever. You can creatively come up with anything, but that doesn't mean that it's valid. If you set up a model where internal energy and temperature both fluctuate, your model's invalid in some way. I don't know that it's horribly invalid, but you are not following the rules of statistical mechanics. What you're calling entropy is not entropy. What you're averaging, if you're averaging configurations of cats chasing lasers, if they're not all the same entropy, they don't all have the same probability, and therefore the averages should not have the same weight. In other words, you're screwing up. All right, so these are the kind of things that are good to know. And again, I don't know that many of you are really going to be solving models, but let's figure it out. Okay, now the microcanonical, all our stats are proportional to the number of microstates, and we work in a world of constant internal energy, volume, and of course number of particles. I haven't been talking about number of particles. I've just been assuming that it's been constant, but now for various reasons I'm gonna start introducing this for reasons you'll see in about 10 minutes. And so, to do anything in the microcanonical, you just need a way to count the number of states. And then you can do things. One of those things is a model that I'm working on today. We always use different ensembles to solve problems the easiest manner possible. So anyway, now, what about this? We can solve things. Let's solve for entropy using the Gibbs entropy formula, which is this. This ends up being kind of useful. Now, this is the same thing as Boltzmann's formula, just expressed differently. And this is probability. And if you recall, I showed you actually at the beginning of this class that this is the same as Gibbs, Boltzmann's formula for entropy. It's really not hard. You say that the probability of state is just 1 over the total number of states. And that's because each state has the same entropy, each state has the same probability. So therefore, if you're doing a microcanonical simulation, and that would be say, molecular dynamics, where the internal energy is held constant, where the volume is held constant, whatever is inside of that box that you're averaging, you can average that property with an equal weight to any other configuration. So what you do is, again, all on a computer, right? You have a simulation box, you have a protein, it's surrounded by water, and you're calculating an average, and you have 1,000, you let time pass so the water molecule moves, you collect 1,000 of these, you get a property divided by 1,000 and add up 1,000 of those properties from your 1,000 configurations, and that's the proper average. Again, that works because you're in the microcanonical. All right, anyway. I know you're thinking, well, what else would you do? Well, I don't know, but don't, because that's the right way to do it. That's kind of part of my point. Okay, so anyway, that's microcanonical. remember that microcanonical tends to be the hardest way to solve things. Not always. Microcanonical is usually not the best friend. Canonical is usually your best friend. It's more intuitive. That's the one that says just count up. You need to know the states, but you need to know the energies of those states. And that way you can get the partition function. So the stats are based on the canonical partition function, which is where beta, which I'm going to remind you is KBT. And of course V and N are still constants. So, and also recall that I was working with the canonical by looking at entropy, but Legendre transforming away entropy's dependence on U and putting it on temperature. Another weird thing about nature, and again, this is something that your PhD physical chemists, nature does not think of temperature. Nature works in a world of 1 over temperature. It was intuitive of us to call absolute 0, 0, but what we should have called it was absolute infinity, and what we think of as infinitely temperature, we should have called it 0. We could have defined what we call temperature as 1 over temperature. If we could go back in time, back to like 1800, when they're giving things names and measuring them for the first time and giving them names, if we just told these people, oh, don't call that, don't do this measurement and report the result, report 1 over the result and call that temperature, then our lives would have been a million times easier. Now remember, what's a meter, right? A meter is about this to my waist, right? What's a liter of water? About as much as I can carry. But does nature think in terms of meters? Nature thinks in terms of nanometers, right? So anyway, what we like units as humans and what nature likes are unfortunately sometimes vastly different. So anyway, okay, so that's, we've talked about partition functions, which is the sum of states. So, you know, the canonical and the microcanonical are really horrifically different because my statistical paradigm has a formula and it doesn't with the microcanonical. Microcanonical is just set up the simulation the right way. Just set up the configuration such that they all have the same internal energy, same volume, that's easy, and we're set. The canonical is, oh, you want to know statistics? Here, get a calculator and do this. It's really quite different. Regardless, and again, I'm going to make this a little bit more solid with actual examples. And the probability of any particular state is the Boltzmann formula, energy over KBT over the sum of all possibilities, which, guess what, that's actually the partition function. Okay, neat thing, I can now solve the entropy. Wait, no, what am I doing wrong? Sum minus KB, sum of states. Okay, again, entropy formula. And now I've got this formula for the probability of a certain state. And, okay, so what does that look like? That is, minus KB, check on my notes. Now, a funny thing is we usually leave the first probability alone, and then we plug in the natural log of the probability right here. And so we end up getting let's see, we'll bring down a minus beta internal energy of the state, which fluctuates. See, remember, I got this little subscript because if we're doing a microcanonical simulation, and let me go back to my molecular dynamics simulation. Molecular dynamics, I clicked on my computer with some software, I drew a box, I filled it with water and maybe a protein, I hit go. It's in the microcanonical. It's automatically in the microcanonical because the internal energy is always set by the equations of motion. Newton's equation of motion, preserve internal energy. Now, instead, in the parameterization of the simulation, you click, no. Don't be microcanonical, be canonical. The program then spits up, okay, what do you want the temperature to be? Now you have to set it. See, in the microcanonical, if you're doing a molecular dynamics simulation, the temperature is fluctuating. Internal energy is the same, but temperature fluctuates. If you want to work in the canonical, then the computer has to say, hey, what do you want the temperature to be? Because I have to set it. And it will add an algorithm to make the temperature not fluctuate. The internal energy is going to fluctuate, however. Anyway, so that's why I have to put a little subscript there. Now I'm lost in my notes. Okay, then minus ln, minus the natural log of q. Okay, minus the natural log of q. Okay, natural log of that going. Natural log of a over b is natural log a minus natural log b. So there we go. All right, so now what? Okay, so this ends up being kb ln q. I don't think I follow the order that I write things very well, by the way, just heads up. I noticed that when I was looking over my notes. Okay, now, okay, minus plus kb ln q, minus plus. Now, when I sum probability times an internal energy, again, for all the reasons I've been blabbering about, where am I at? I should just average internal energy. Okay, yeah. All right, so anyway, the canonical entropy is defined. But now let me just show you this neat little trick. I'll remind you that ln, so I'm just trying to remind you about all the stuff that we've been covering. Natural log of the canonical partition function is minus beta a. And we did solve that. I don't want to show that again because this is a review. And a, by definition, is a Legendre transform. Okay. A is U minus TS. U has internal energy, has entropy as its natural variable. If I want to get rid of that and place it on temperature, actually just 1 over temperature, we subtract that away. Okay, so now I have to use average U because again I'm working in the canonical and there is no U. Let's see, okay, now let me go back to this guy. This is why I hate these freaking boards. Okay, so now I've got KB LNQ so I don't get confused. Okay, so KB times that minus beta U plus KB beta TS plus beta oh, yeah, no, I'm not lost. This is as is. Okay, you may notice that I have canceled out these two terms, and I'm left with KB B beta, KB beta TS. What's that? Beta's 1 over KBT. Huh? Yes. Yeah. I'm just messing with you people, by the way. I started with entropy, I ended with entropy. I'm just messing with you, just to show. But it does show that this stuff works. That's kind of important, so that's nice. Let's see, what else have I got? All right, so I'm still working the canonical. And again, I just want to remind you of all the neat stuff. Remember, part of the point here is that with this statistical definition of entropy, canonical, microcanonical, whatever, I can manipulate stuff to get all my thermodynamic information. Here, I have some neat here. I like that board. I know that the change in the natural log of Q with respect to beta is the average. I think I've already done that. And the double derivative of ln cubed with respect to beta is kBt squared. Heat capacity, and this ends up being the variance in internal energy. Okay, now remember I said I'm always kind of floored. Heat capacity is something very measurable. It's what all calorimeters do, and it wouldn't exist unless internal energy fluctuates. And an interpretation of this is that if we could shrink ourselves down, and let's think about that molecular dynamic simulation of water. Maybe there's a protein, there's not a protein, whatever. Imagine that again, we shrink ourselves down and look at water, and we look at just a couple of water molecules. Water is going to interact with about maybe 2 or 3 other water molecules at any given moment, and it's fluctuating because they're bumping into each other. And that chaotic bumping and rolling and whatever, that's entropy, by the way. And because of that chaotic, that chaotic motion, that chaotic interaction on a very small length scale, that is this. That's what that is. That chaotic motion leads to changes in your interaction. And of course it does, and that's what that is. But that's where you get heat capacity. Now it turns out that we can go through all the rigorous proofs of every kind, but it's almost universally true that for every average of whatever variable, the derivative with respect to its conjugate is equal to the variance in that variable. The variance is squared. Right. It's a standard deviation without a square. The average standard deviation is 0 of anything. Standard deviation is what are you minus your average. On average, that's 0, because that's what averages do. That's why you square it to 0. Anyway, and here, heat capacity is, of course, changing energy with respect to temperature. So, temperature is 1 over temperature, is conjugate. Anyway, so now what am I doing? Yeah. So now I want to go back and try. That's a long-winded review. My class, when I teach undergrads, my class is incredibly slow because I tend to review, like I did now, I just reviewed half the freaking class. I tend to do that, but whatever. And another problem that happens sometimes is I get lost in my notes. Okay, now again, I promised that I would show off how you can calculate things in the microcanonical and things in the canonical, and they have to be equal to each other, and always one of these ensembles is going to give, they give the same answer, but one of them can be quicker than the other, and that's why they're useful. All right, and I've spent, we're a little over 1/3 of the way through the semester, and knowing about partition functions and ensembles is hopefully quite useful. I mean, it's embarrassing for you to graduate with PhDs in physical chemistry and you don't know what ensembles are. That's just weird. But you also need to know what relationships are revealed by them. I just talked about fluctuations in internal. I know I hark on that because it's so neat. But anyway, population and heat. These are huge, and you're about to see that. This is one of the biggest things I could ever tell you about. So now, remember I told you that we're going to have a system, a 2-level system. So this could be the band. if the band gap, God, I'm using specific terminology already. Let's say that there's a ground state and an excited state with epsilon energy, and there's a couple of things that behave this way. One would be NMR, where spin aligned with spin anti-aligned with the external magnetic field would be the ground state, and pointed the wrong way is an excited state. That's a 2-level system. And you could populate, and so again, I said I would populate them with whatever they are. So if I'm talking about NMR, these are protons, spin up and spin down. And there we go. And I will have N particles, or spins if I'm talking about NMR, and M are excited. Okay, now this could be a semiconductor, in which case this would be the valence state full of electrons, and that would be the conduction. Yeah, and that would be the conduction state that can get electrons if I excite them thermally. We're doing thermal, and therefore internal energy. And notice I'm already working. I'm already working in the microcanonical because I've defined internal energy. I'm not saying the average internal energy, I'm saying this is internal energy. I'm in the microcanonical automatically, because I cannot say this in the canonical, I have to put the average signs. Okay, so I've decided to go to the microcanonical. Now I need a way to count states. If I can't do that, I got nothing. Okay, what are the number of states? It turns out that now we did cover this last time. I look at Wikipedia and I look at permutations on, in this particular situation. N total population, M is partitioned into one side, what are the total number of ways I can do so. Of course, factorials. I remember at one point in high school learning how to do those kind of permutation mathematics. Obviously, there's always a factorial. I don't remember how to do it anymore. I just looked this up on Wikipedia. Okay, anyway, and of course that means that entropy. So there we go. I've already got one thermodynamic variable, and that's this. And this is brainless. I covered this last time. But I also mentioned Stirling's approximation. Again, one of those things that if you don't know about as a physical chemist is embarrassing. Notice I'm just writing these without notes because I know it so well. Natural log of a factorial is x ln x minus x so long as x is big, and that means x is like 100 or so. Plug it into a calculator and see. When we're talking about n are molecules, so they're often around 10 to the 24, 10 to the 26. So this isn't really an approximation, not if the error is like 1 over 10 to the 19%. That's just not wrong at that point. Okay, and for those of you sitting over there, how do I want to do this? I need a, okay, let me do one more thing here. Okay, in this case, S over KB, and then I'm going to do a derivative over there. Okay, let's see, I got N ln N minus N, so I did the top part, so I divided by KB, ln A minus ln B, and ln A is N ln N minus N. Anyway, I moved to the following okay, now I've got to do the stuff on bottom, and the stuff on bottom, everything picks up a minus sign. ln A over B is ln A minus ln B. And, none of this is particularly hard. It's just a lot of don't get lost in writing 20 terms. You mess up one of these, unfortunately, you're permanently lost. Okay, on the second set of terms, that minus x ends up being plus because n minus n factorial is on the bottom. Okay, so that is that. Okay, now the neat thing is that the change in entropy with respect to internal energy is 1 over kBT, which of course is beta. And U is the number of the excited state times the band gap. Okay, I know you're struggling to see. So what I'm going to do is I'm going to take the derivative of this with respect to m. Epsilon's a constant, it can come out. I'm going to take the derivative of this SOB with respect to m, and that's going to give me the temperature. 1 over temperature. Again, nature doesn't think in temperature, nature thinks in 1 over temperature. So don't forget that. Again, big picture, I have kind of a realistic model for a lot of different stuff. I haven't really made any approximations other than to make this model, which I imagine corresponds to really a lot of real stuff. A model for internal energy, a model for entropy, and then the derivative thereof gives me temperature. So that's the idea. Okay, so unfortunately, because I need so much room to write this is what I hate this thing, because I have to do that sometimes. I just can't write across with these two things here. This is the stupidest room in the world. Anyway, God, I'm so full of anger. Okay, so 1 over kBT, yes, this is beta, by the way, is the derivative with respect to ME. Epsilon is a constant, so it can just come out. I'm going to write it all out again so that you can... wait a minute. You know what? I'm going to eliminate what I wrote before and just did. I'm going to eliminate every term that doesn't contain the letter M, because it will not survive the derivative. So that n, ln, n minus n is now gone. Hopefully, just at your notes and you know what I just said. Okay, so again, I just eliminated any term in what I just wrote that does not have a letter M, because it's going to be gone when I take this derivative. Okay. And I had made a mistake because this is ridiculous. Yeah, there you go. Don't be shy if you make a mistake. That's stupid. Okay, now. What the hell are you doing? Okay, now again, don't be weirded out when you see funny derivatives. The derivative of a function with respect to 5x. Take the derivative with respect to x and divide by 5. That's totally legit. So anyway, that's what I'm doing here. I'm taking out this energy gap, which I have defined in my model. And so then I'm taking the derivative with respect to m, and again I have to, online when I was your age, these symbolic differential calculators and integral calculators were just starting to exist. You had to MathCAD. It was a little bit of a pain to use, a Mathematica, which was a lot harder to use. But the guy Larry Wolfram, who started Mathematica, he's actually put it all online for free. I guess that's what rich guys can do. Anyway, so I know I can do these derivatives, but again, I have to emphasize the trick, if this was an exam, is just to be ultra careful. So you can do this, you just got to be obscenely careful. And I remember looking at this before class last week, actually, because I thought I was going to do this last week. And I was able to follow it. Let's maybe just take a quick look at it. Just take a quick look at it, just for the hell of it. Okay, so the derivative of this term would be, let's see, so I have the n, because that doesn't get hurt. The derivative of ln x with respect to x is 1 over x, so 1 over n minus m, but times the derivative of the inside, which is minus 1, so that's why the minus sign is gone. Okay, okay, now this is a product rule, so the first time I take the derivative with respect to m with respect to m, leaving just this. The next time I'll leave m, but take the derivative of the other guy. which is the same thing as what I did over there. These have been canceled. Yeah, look at that, that's brainless, right? And then the derivative of this guy with respect to that one leaves ln m, and then I have to take that and then take the derivative of that guy. There we go. All right, so anyway, so it makes sense. That's not impossible. But
over there, you put a minus. Minus M over. Your plus, right?
Something plus, doesn't it? My notes say minus. What have I?
And then it's minus up there.
Minus there. Wait, no. Wait, hold on. No, this is okay, because that, what are you saying, this should be positive?
Yeah, because.
No, this is,
Oh, okay,
that's
okay,
gone.
no.
Remember, that canceled that.
Okay.
Right, and this, no, I got that.
Okay.
Anyway, all right, so, now do stop me if I make a mistake, because that sucks. I have to spend a bunch of time next time. Let's see, okay, these two terms combine, by the way, and let's see. So that's n minus m, because they both contain the same dividend of n minus m, which is now 1, minus m over m. Okay, so that did real well. Kill, die, and that leaves me with ln n minus m over n. I just combined ln a minus ln b is ln a over b. You've heard me say that a couple of times. Okay, so these have canceled, and so I get 1 over epsilon ln n minus m over n, which is, I'm going to just simplify that, 1 over epsilon ln n over m. This is just algebra. And I want to remind you that this is 1 over kBT. Because I'm taking the derivative of entropy with respect to internal energy. Question?
The little n at the second to bottom row. Is that supposed to be big N? Or
yeah, sorry, there is no little n, right? So thanks for pointing that out. Yeah, there you go. Yeah, with undergrads, this is impossible. They'll never stop. Never stop me. That's pretty bad. Okay. Now I want to point out that my favorite trick in the world is to multiply by the number 1, and what I've got is an epsilon over internal energy. And so now what? Now I've got, where the hell am I at? Now I've got 1 over kBT, 1 over kBT is equal to 1 over epsilon, I'm writing this in the wrong order, ln, n over m is n epsilon over u minus 1. Okay, all right, that's a nice formula, but so what? What I want to do is then solve for u, which again is just some algebra. It's actually like 2 steps. You can solve this in 2 steps. Epsilon over kBT. Okay, this looks awful. Okay, which is n epsilon over 1 plus e to the beta epsilon. Yeah, no minus. Right, no minus, sorry, there you go. Okay, so internal energy is equal to this. Now, what I've done here, so what I've been able to do here is, this, I have to admit, this always twists me up, because I told you that the thing about the microcanonical is we fix all this stuff. Well, because I solved this model, I fixed n and m, but m could be anything, so I haven't. but I did because I gave it a letter, but I didn't because it could be anything. And that's weird, and I can't ever get over that. Anyway, so with a fixed n and m, it's true that u is also fixed, but since I haven't said that, n is 50 and m is 25, I haven't said that, then in a way it's not fixed. And that allows me then to calculate u actually as a function of temperature by all this statistical mechanical magic. So I never can kind of get over that. This is like one of the most famous derivations that exists in stat mech. And it's just weird because internal energy has to be fixed, yet it's not fixed in any way. So, and since I'm just a babbling idiot, let me show you what this means in terms of temperature. Let me just write this again, and then we'll be done. And then actually what we're going to cover next time is there's a third ensemble. So you learn canonical and microcanonical. There's a third. It's called the grand canonical. And what that does is that allows chemicals to react into other chemicals, or ice to melt. What we're going to do next time is solve PV equals nRT. So that's, again, one of the more famous derivations. Let me write this again. And epsilon, and then I'm going to graph it, which is going to do some things that are kind of neat. Okay, now, let's see, if temperature was 0, what are we getting? Beta, if temperature is 0, what's beta?
Infinity.
All right, what's e to the infinity? It's infinity. Right. Now, of course, what happens? Everything's in the ground state, right? If temperature is 0, everything's in the ground state. Of course it is. Okay, now, this is where it gets cool. If I raise the temperature to infinity, is everything in the excited state? Before I solve it, is everything in the excited state? Well, now shouldn't it be? Now hold on, I'm going to throw infinite amounts of temperature. Now these particles will enter the excited state. Of course they won't. You have to do something with the temperature. So they'll all be in the excited state, right? Doesn't that make sense? Isn't that what a middle schooler would tell me? Are you smarter than a middle schooler? Okay, let's do that. T goes to infinity. Okay, what is e to the 0? 1. Okay, so u is n epsilon over 2. Okay, now, if all n particles were in the excited state, the internal energy would be n epsilon. The internal energy is n epsilon over 2. That means only half. Only half make it. You can heat this SOB up to infinity, and these things stop when they get to the halfway point. It is a paradigm in physical chemistry that when you're populating excited states, you can never get past the halfway point no matter what. Now, what if I used, so this is true no matter what. What if I used a laser? Can I do it then? So instead of heating it, I use a laser. Now at that point, if I'm blasting every one of these particles with a laser, can I beat this problem?
Not in two states. Yeah, not in two states.
Not into two states. Now why? Because they'll fluoresce?
Or relax in some format.
Well, they'll relax by Einstein's method, which is that the light eventually induces depopulation with equal probability that it induces population, which is how lasers work. So you have to beat that. But anyway, so again, in physical chemistry, you should know, unless you do some clever tricks, you can never populate excited states beyond the halfway point. It's impossible. And now let me point out another thing. Let me plot S versus U. And here we have 0, and epsilon over 2, and n epsilon. Now, I have you've already seen a couple of formulas for entropy. What's the entropy if internal energy is 0? Where everything is, there's only one configuration, everything in the ground state. There's not 2 ways or 3 ways or 4 ways. There's only one way to draw this. So what's the entropy? Well, that, KBLN what? 1. There's only one way to generate this configuration. The entropy is 0. Okay, how many ways are there to generate a picture where all of the particles are in the excited state? Right. There's only one way to do it. So our entropy is going to go from 0 to something. Well, here, let me just draw it. I just want to point out that you have a ways of getting at least 2 of the points. This is what the entropy looks like as a function of population or internal energy. Or I guess I can figure out with respect to temperature too, but anyway. Temperature, yeah, what am I saying? Temperature is actually the slope of this line. Right? Of course it is. 1 over the slope. 1 over the slope of the line. ds du is beta, 1 over temperature. ds du is the slope. Beta is 1 over temperature. Again, nature thinks of 1 over temperature. Okay, so 1 over this slope is a number, but this slope is 0. What's 1 over 0? Okay, right. So there you go. So you can never get past the halfway point. Now, as I also promised you, what would be the temperature over here? What's that temperature? It's negative. Remember I told you I can show you how to create negative temperatures. You just can't get there. And that's because entropy would actually, that's the reason it's a negative temperature is that as you add energy, entropy decreases. You can't do that. Now, if you can do that, you'd have negative temperatures, but for all the reasons I just showed you, you can't do that. So this is why you can't get past the halfway point when you're trying to populate excited states, because you'd have negative temperature. You just can't do that. Okay, so last bit I wanted to cover is that we do have ways of beating this problem because we're clever, but what it requires, and this is for lasers, are 3-level systems. Okay, so now let's make this an electron, and this is a single molecule. This is a single chromophore, and what happens is, so I have a mole of these guys right now. Now remember that once I've excited half of them by temperature or a flash lamp, however means, once I try to excite the n over 2 plus 1, what happens is actually one of the excited ones just relaxes instead. Okay, now what happens is, for us to build a laser, we have to use molecules or atoms, like neodymium, that's an example, that will relax to this state. Okay, very quickly. And then, see what happens is, it's like feeding an elevator where I just add population at this excited state, but it depopulates so quickly I can keep adding it. And it depopulates to this state, which then fluoresces or stimulates emit, which is how I can actually get a laser. This is how you can get population inversion, is to cheat. You actually have to have a second level present to depopulate the excited state. And then you can get population inversion just of the substate. And that's how you do it. And there's a couple other tricks too, but anyway. All right, so next time is going to be super exciting. PV equals nRT. Now, instead of proving it by, here's Boyle's law, pressure is proportional to volume. Here's Charles's law, pressure is proportional to temperature. Instead of that boring stuff, and then you just combine them into PV equals nRT. That's not a proof, right? That's an empirical combination of several things that makes sense. To prove it, you have to do this kind of jazz. And the only way to prove PV equals nRT is statistical mechanics. The density of a gas to fluctuate. You realize that's the laws of density fluctuations in a gas. For that to work and follow these rules, PV equals nRT.